Hello, this is your Unit 10 study guide. All right, so the first one says, write out the first four terms of this sequence starting at n equals 1. So you just have to plug in 1, 2, 3, and 4 to list out your terms. So if we plug in 1, we're going to get 3 to the first over 1 factorial will just be 1. So we get 3 for the first term, and then plugging in 2. So 3 squared would be 9, 2 factorial will just be 2. Plugging in 3 cubed would be 27, 3 factorial would be 6. And then plugging in 4, 3 to the fourth would be 81, 4 factorial would be 20. So you're just plugging in 1, 2, 3, and 4 and just making a list of numbers. That's all that is. So 2, write an expression for the nth term of the sequence, note when n starts. And you would start it at 1 or 0. So what you want to notice about this one is that it is geometric. We're multiplying by -2 to generate the terms in the numerator, and we're multiplying by 5 to keep the pattern going for the denominator. So your first term is that 2/3, and our R value is -2/5. So when you go to write out an expression for the nth term, you're going to have a sub n equals that first term times R to the nth. And for geometric, n starts at 0, so n bigger than 0. All right, make an example of a sequence that is monotonically decreasing, so all the numbers have to always be getting smaller, and converges to 3. So when you do the limit as n goes to infinity, you just need for that to go to 3. So you would need something that looks like this. The problem with that is these n's would cancel and you would just get 3. So your sequence would be 3, 3, 3, 3, 3, which actually wouldn't converge. Well, it is, I guess it would converge to 3. It's just always 3 all the time. But it wouldn't be monotonically decreasing. So you have to add on some other number here. I'm just going to add 1. You can add 2 or 3 or 5 or 700. It really doesn't matter. You just can't subtract. If you subtract, you'll find that the values would be increasing instead of decreasing. So let's just list out a couple so that we can kind of check it. I mean, this is all I would really need for the test, but it's never a bad idea to just like list out a few so you can check it. So if we plug in 1, we're going to get 4. If we plug in 2, that would be 7 halves. And so you can see already they're going down. Like this goes from 4 and then 7 halves would be 3 halves. And then if you plug in 10, you're going to get 10/3. And if you plug in 4, you're going to get 13/4. And you can keep going. I just like to list out a few just to like check, just to make sure it actually is decreasing. And these are getting closer and closer to 3. So like if you think 9/3 is pretty close to 3 and then 12/4 is pretty close to 3, it's going to keep on going and get closer and closer to 3. All right, so this one, determine if the sequence converges or diverges. If it converges, find the limit. So you really just need to do limit as n goes to infinity for this. So with this one, the problem is you're going to get infinity over infinity. Like it's just going to keep getting larger and larger and larger and larger. So this is going to go to infinity. And so that diverges. So in other words, the list of numbers isn't headed anywhere. Like this one, these are getting closer and closer to 3. This one's just going to keep getting larger and larger and larger forever. This one, I would more think of it as like alternating. It's going to alternate -2, -3, -2, -3, so on and so forth. So it's not headed anywhere. And so one also diverges. If it did converge, like this one would just like say you got an answer, like say you did the limit as n goes to infinity and you got 7, then it converges to 7. It's just neither of these were headed anywhere in particular, so they're both diverge. All right, find the first 4 terms of the sequence of partial sums for this series. So sum of the first term, that's just going to be the first term. So we're just going to plug in 1. So 3 to the first would be 3. 1 plus 1 would be 2. 2 factorial is 2. So 3 halves. So you're summing up the first term. So it literally just is the first term. Sum of the first 2 terms. So we're going to take the first term plus the second term. And I'm not going to reach for a calculator until I have to, but I have a feeling these fractions are going to get real messy in just a minute. All right, so if we plug in 2, 3 squared would be 9. 2 plus 1 would be 3. 3 factorial would be 6. So that would reduce to 3 halves. So 3 halves plus 3 halves would be 3. right? Summing up the first three terms. So this would be the sum of the first two terms. I'm just going to carry that 3 down to the next line, plus the third term. So this is the first two terms added up to be 3. Now we're going to add on the next one. Every time you just keep adding on the next one. So plugging in 3 cubed is 27. 3 plus 1 is 4. 4 factorial is 24. And yeah, I am going to reach for a calculator on that one. Let's see if that comes out too. All right, 33/8. And then I just said the first 4. Okay, so we got to do one more. So summing up the first 4 terms, well, this is the sum of the first 3. So just bring that down. And then we have to add on the 4th term. So 3 to the 4th would be 81. 4 plus 1 is 5. 5 factorial is 120. So I'm just going to add those together. I got, wait, did I mess something up? Hold on, let me make sure I typed it correctly. It just didn't feel right. I think it is, but let me make sure I typed it right. Hold on a second. Yeah, there we go, 24/5. So each time you're just adding up, like this is adding up the first term, it just is the first term. Here you're adding up the first 2, adding up the first 3, adding up the first 4. So that's a partial sum. All right, so number 6, an infinite series has an nth partial sum of this. What is the sum of the series? So we're just going to take n out to infinity for this. And so these are both n. We're going to use the coefficients, and so 3/5. So that's all that there is to that. And that's kind of what I was saying about this one up here. Like if this had come out to just a value, it would converge to that value. And that's what's going on here. All right, so all of these are geometric series. They are going to converge if your R value, the absolute value of your R value is smaller than 1. They're going to diverge if your R value, your absolute value of your R value is bigger than 1. All right, so for this one, first term is 4. And our R value, it looks like we're multiplying by -1/3. So that absolute value is smaller than 1. So we are going to be able to get the sum. And your formula is, it is A over 1 minus R. Now I do want you to simplify these down. That would be 4 over 1 plus 1/3 would be 4/3. So that's 4 times 3/4. You're just going to flip that over. The 4s are going to cancel. And so you'll just get 3. All right, for this one, our first term is 5 and our R value is 7/3. So that's bigger than 1. So this is going to diverge. So diverges because R equals 7/3, which is bigger than 1. All right, these two look really strange. We're being told that they're geometric though. What I would do is list out the first few terms so that it looks more like this one. It's nice if it's written like this. This is just your first term and then this is R. But if it's not, you want to list out the terms so that you can kind of see what's going on. All right, so let's plug in 1. 1 plus 1 is 2. 3 squared is 9. And then denominator will be 4. So 9/4. All right, plugging in 2. That'll be 3 cubed is 27 or 16. Plugging in 3. That'll be 3 to the 4th is 81. 4 cubed is 64. And that's good enough. Just do like the first 3 or 4. This is good. We can see the first term is 9/4 and the R value is 3/4. And so since 3/4 is smaller than 1, this is going to converge. And so we're going to find the sum. It will be 9/4 over 1 minus 3/4. That'll be 9/4 over 1/4. The 4s are going to cancel. 9 over 1 gives you 9. All right, and then this one, same thing. I'm going to start by just like listing out a few of these terms. So plugging in 1, that's going to give us -1 over e cubed. Plugging in 2, that's going to give us +1 over e to the 4th. And then plugging in 3, we'll have -1 over e to the 5th. And that's good enough. I can see what's going on there. So first term is -1 over e cubed. And R value, we're multiplying by -1 in the numerator and e in the denominator. So this one's going to get a little bit messy with like simplifying this, but same thing. We're going to take the first term over 1 minus r. So those negatives are going to cancel. It'll be 1 plus 1 over e. So actually, I'm going to erase this 1 and write it as e over e. So I have a common denominator there, and I can put these together. This is like fun with algebra here. So negative 1 over e cubed, and then this would be e plus 1 over e. So one of these e's would cancel, would end up being e squared in the denominator. So we're going to have negative 1 over e squared times e plus 1. All right, number 8, apply the nth term test for divergence and tell what that means. So we're going to do limit. These ones are using k instead of n. So limit as k goes to infinity of all of this. So since these are both k cubed, we're going to use the coefficients. 2 over 1 would be 2. So if it comes out to anything other than 0, that means the series diverges. So the series diverges because the limit is not 0. Right, so for this one, we're going to do the same thing. Limit as k goes to infinity of all of that. So the numerator is polynomial. When you have, your variable squared or to the third or to the fourth, that's polynomial. This one is exponential. Our variable is in the exponent. So this one's going to grow a whole lot faster. And when the denominator grows faster, it's going to go to 0. Now, unfortunately, that does not mean that you conclude that the series converges. If you don't get 0, it means it diverges. But if you get 0, then it's no conclusion. So no conclusion, because the limit is 0. So that's unfortunate. If it comes out to anything other than 0, you get to say it diverges. But if it comes out to 0, you don't get to make any conclusion. You would have to try something else. All right, number 9, determine whether or not the series converges. State your reasoning. Both of these are p series. So for this one, p is 1/5. For a fifth root, p is 1/5. It's backwards from the geometric series. For geometric, if r, absolute value of r, was smaller than 1, it converged. For the p series, if p is smaller than 1, it diverges. Bigger than 1, it's going to converge. So this diverges because p equals 1/5, and that's smaller than 1. This one, p is 5. So this converges because p equals 5, and that's bigger than 1. So you just have to remember the geometric and the p series, the rule is opposite of each other. And then last one, we're going to use the integral test to determine convergence or divergence of this series. So it'll be limit as b goes to infinity, integral from 1 to b of this, and I'm just going to change the n to an x so that we can put a dx at the end. So if we get a result here, like you get an actual number, that means it converges. They either both converge or both diverge. If we get like infinity, that means this diverges. But even if we get a value, that doesn't mean that that's what this converges to. It just means, yes, it converges. All right, so limit as b goes to infinity, and we're going to do the antiderivative. So you can, it's a u substitution, and you can write out all the steps if you want, but you're going to need a -2 as your adjustment there to cancel out the -1/2. So -2 e to the -1/2 x, such that 1 to b. Keep writing your limit. We're going to do upper boundary minus lower boundary, and then the last thing we'll do is evaluate the limit. So plugging in b, this would be -2. I'm going to bring it down to the denominator. The negative exponent means that would be in the denominator. So e to the 1/2 b powers in the denominator. And then here, if you plug in 1, that'll be -2 e to the -1/2. You can bring that one down to the denominator too if you want, but the reason I wrote it for this one is so you can see when you evaluate the limit, you plug in an astronomical number here, your denominator is getting super, super huge. So this portion goes to 0, and then these negatives will cancel. So +2 e to the -1/2. So it just equals 2 e to the -1/2. So we got a value, and so we conclude that this converges by the integral test. And again, the series won't converge to this. It's just if this converges, if this integral converges, then the series does as well.